Check. I assume the Zoom can hear me okay? And then everybody else can hear me okay? Okay. Good evening, everybody. Thank you for attending and giving us this opportunity. Hopefully, the food being delayed wasn't too long and everybody did get something to eat. So thank you for attending, as I say. So this evening, I'm going to have a look at scaling seamlessly, but in the context of multi-architecture for in the realms of Kubernetes. So, and specifically where Cape can help from that side. Oh, sorry, that's it. So, firstly, about me, I was an engineer. It has been a couple of years since I've written production code, to be honest, but I have always had the view from an engineer's perspective. I do look after the product engineering side for Cape, so still keep my hand in that way, but not so much on the production side anymore. Cape itself is a product that we brought to market to simplify the deployment aspects of Kubernetes, and especially in those areas of multi-architecture and other key areas. But I'll give you a little bit more detail later in regards to that side of things. So as I say, today, I just want to go through the multi-architecture, why multi-architecture, some use cases around it, challenges, how Cape, and actually along with Docker Build Cloud, can assist on that side. And then a short demo, just a short live demo from that aspect, hopefully not take too long, just to run you through. And then if there are any questions in the room. So first off, I suppose the question is, by a raise of hands, is anybody currently using or considering moving towards an ARM-based architecture, or is it still pretty much based around the x86 Intel? There's one or two. So it is moving this in this way. Big driver is obviously cost, but there are other aspects of it. So specifically looking at how those use cases are now coming and how we can assist on that side. So there is obviously a rise of the sort of heterogeneous infrastructure, that mix of ARM processors, whether it's AWS's Graviton offering, but also Azure have their own offering, Google are going into their own offering as well. There is also in the aspects of sort of edge IoT devices that are out there as well. So it is becoming more commonplace that there is this mix of architecture sitting below the virtual instances, and needing to understand how to work in those environments and what can catch you out, what can be the benefits and so on from that side. But it is becoming more commonplace. A lot of the CSPs are pushing it more and more for their offering when it comes to various instance types and so on from that aspect. To give an example, just on the cost-based side of it, so AWS themselves are obviously highlighting as much as possible from the Graviton and up to 40% cheaper from deployments and running those instances. So it can obviously be a very good cost saving. But not only with that cost saving, there is also other areas that do take impact on that side. I suppose one of the other key aspects is the energy efficiency, which also does go away to sort of managing sustainability questions as well on that side. But there is quite a lot of information and studies out there to show how, from an energy, from a cost, and particular use cases as well, can benefit towards moving towards the away from the standard architecture that most people are used to with the sort of Intel x86 and on to the ARM offering. And again, this is only just from an AWS perspective. It is similar when you look at the other cloud providers and how they're offering it as well from that side. Some of the key elements to this is obviously adaptability. You are benefiting, and if you can adapt to it, you are benefit from what the CSPs themselves, how they're innovating along those lines. The hardware, as I say, is evolving. So a lot of the data centers are being built out to utilize different types of hardware architectures. But not only just from the cloud perspective, there is obviously that move towards are covering the sort of hybrid infrastructure as well. And if that is getting into some people with lower powered devices in the IoT world and the edge world as well. So being adaptable and being able to utilize that is obviously one of the key things that just to ensure that you have consistent offering tooling and ways of deploying utilizing that hardware. So it is a very key element to ensure that you can adapt to what's being offered there and taking advantage of what's out there at the moment and to come. So some of the use cases, some of the top use cases that are out there, people look at specifically when they're looking to see, okay, will I use a different type? You have the elements from the website, from containerization, the orchestration of services, and so on across there. Data pipelines, I'm managing those, caching, and so on. I have added one other, which is not specific to sort of the ARM architecture, but just more along the lines in regards of having a different need for your services or your containers to run on, which is looking also at the GPU side of it. So when you have services that are doing some deep learning or training, you might want to obviously push those services towards the GPUs as well as the CPUs. So I've included this in the sense of multi-architecture as opposed to the difference between ARM or x86, but the same sort of concept lies there, that if you have certain workloads, you have certain services that you do want to push across, having the right tools to do that is obviously key from that aspect. So it's not a simple thing. It can be made simple, but obviously to ensure that we make it as simple as possible, there are areas to look at and be very conscious of. Obviously, the build and the deployment pipelines is one of the key aspects of that. That's obviously a key aspect that we are looking at. From a build perspective, there is building the containers, building workloads for the right architecture. If you're doing that locally, how do you support the engineering team if they're using local builds? It's all nice if everybody's been issued brand new MacBooks and things like that there that are running the right chipsets to emulate, but with large teams and things like that there, it's not always the case. So how do you have those build environments to ensure that you can build for the different types of architecture and then obviously deploy across that and ensure you're pushing the right images to the right hardware and so on from that. Obviously dependencies, making sure you're pulling the right code and so on, and any cross dependencies that you might have, how do you handle that? And just the operational overhead to manage. If it's all being pushed to one type, then it's a little bit simpler. But when you start getting in and having to understand what's being pushed and what you're actually running on, there is overhead that has to be managed across that. So these are things that obviously need to be looked at from that aspect. So what we're looking at is simplifying that. Well, there's two steps to that. There's obviously one of the areas that we as CAPE are very keen on, which is the deployment side. But just an example from a build side, and that aspect of how do you ensure you can build when your local environments are maybe based on Intel chipsets and so on. So with utilization, the likes of Docker Build Cloud, that gives the ability that your teams don't have to move to newer hardware and so on. You can build using a mix of your desktop engine, your Docker desktop, right the way to Build Cloud, and have your whole pipelines built that way. But then what happens when you're wanting to deploy from that aspect? So as we obviously from our side, utilizing CAPE simplifies that process of knowing which architecture to push to, being able to pull your images out of the different registries to make sure that you're grabbing the right ones and so on. And then doing all of this within your current pipelines without having to make big changes, having to rewrite everything and so on. So trying to integrate as simply as possible just to ensure that you're not having to refactor, rebuild your whole pipeline to do this. So this is obviously the key area that we focus on from this side. So what that actually looks like, as I say, from the build environment, one of the key problems is that aspect of can an engineer build on their machine, or do they need to push to a different environment to build the various images that are required? Docker and their various tooling does give that ability, which is great. But once you have those images, whether it's in Docker Hub, whether it's in your AWS registry, or whether it's in Azure registry, it doesn't really matter from that aspect. CAPE then obviously allowing for the deployment and then enhancing those deployments that you would have in your pipeline, whether it's through your various progressive delivery, pre-flight checks, just ensuring that what you're going to deploy is right, and then obviously pushing it to the correct infrastructure, and ensuring that as much as possible, each deployment and each delivery is as successful as possible from that side. And then in this particular scenario, pushing out to the various infrastructure types from that side. So with that, I'll just give you a short demo. We've obviously kept this relatively simple so that we're not spending time watching builds going on, things like that there. So I'm not, actually, why is that not switched? 2 seconds. Second. Okay, switch. It's just out of the way. Okay, so as I say, just a very short, simple demo just to give you an idea. We're not going to focus on the build side because obviously, as I say, we don't want to spend time just watching a build happening from the side. So assumption being that the build has happened, I'm sitting there, the images are sitting there ready to go out. In this case, I'm just going to make it, as I say, very simple. We have a fleet of clusters that are based on x86. We have a fleet of clusters based on ARM. We have those laid out. And I'll just do a very simple split to push the right images in the right place from that side. So in this case, from a cluster perspective, we have, as I say, cluster groups where we have a x86 fleet and an ARM fleet. So as you need, you can just pick up the clusters depending on their architecture and push what's needed from there. So I'll just start a deployment from here. So in the world of live demos, so we've a couple of web shops that we'll push that are sitting here at 404s at the minute. But we'll just do a straight split. So within Cape, we'll just choose the AB to do that. On this side, we'll just I'm using a new laptop, so it didn't have my storage values. Just choose our application, choose that we want to go to the various fleets. So on this one, we'll choose to go to the ARM fleet. We'll choose to go to the x86 fleet. So on this one, we'll tell it that it's the ARM. On this side, we'll tell us the x86. I could choose to push them into different namespaces if needed, but in this case, we'll just keep it very simple from that side. Once I do that, you'll see here just additional information. These add-ons are for the same for going either route, but just very quickly on the main route, we've a number of recommended actions that can be taken, whether it's pre-flight checks you want to do in the sense of, I want to check that Nginx is preloaded or Postgres is preloaded, whatever you need from that side. Whether you're the one doing the deployment, but somebody else has written up the manifest, you want to check to see, just to do a dry run, just to make sure actually what have they changed. Somebody else has been doing that part, just really understand what they've changed. Scan for the latest to understand what the difference is between the last time a deployment was created. Also put local variables, push through if they're required. Typical things like if you're changing HTTP ports or HTTPS ports and so on, you can push those through for each one of those. One of the other aspects, because we do look at the multi-architecture, the ability to deploy anywhere, we do specifically look around edge deployments. As we all know, sometimes you push a deployment, you go, is this going to take 1 minute or is it going to take 10 minutes to really understand? Do I go for a coffee and come back and still happening should have happened? Just a way to get an estimate of, okay, well, we know the images are X size, what our bandwidth would be from that side. If you're pushing out to remote sites and so on, just to really get an idea from that perspective. The small features, so as I say, A and B, because just the two splits, but I'll jump through that. The last part, again, in that aspect of what we do from an edge perspective, it may be that you have intermittent connectivity to certain sites. You can set priorities. So if it's updates or if it's specific packages that you want to push, that if you have a limited connection, that it can sit and wait. And when it gets connectivity, push whatever's the highest priority from that side. So in this case, we're not worried too much about that. So we create deployments. We should have success on that side, new deployments. And then on this side, all being well with live. So this is just obviously a very simple example, just to show, in this case, we've just highlighted the different infrastructure with color coding red and blue, just to give an idea without having to push through to look at the underlying. But just to show you how simple with Cape, and obviously that's driving through the UI and being able to do it through the UI to really simplify for engineers coming on board. But there is full automation sitting behind that to integrate into your pipelines. Once you have that done, you can grab and just give you an example. Oops. If you were looking for your CLI information, you can grab the CLI information directly out and patch it into your automation from that perspective. So as I say, that's a very simple, quick demo to give you an idea of Cape and how it can assist. So how it can assist from a multi-architecture perspective on that side. The last thing, just to wrap up before any questions, is we do have a Cape pilot scheme, which we run free of charge for your teams. Um, it can be 2 to 6 weeks, depending on how much time you want to run on it. It's completely unlimited, so you can actually put it directly into production and utilize everything. We dedicate resources and everything to it. We are an enterprise tool, so support and resourcing and so on from that to work with your teams is out of the box from that side. And we do like when we do the pilots, we do like to work with the teams to do that. One thing that we found in the past is sometimes if you give it to a team, uh, they're not sure exactly what they should be testing against to see the improvements they might be doing in the pilots and so on. So we do work with the teams. We can work out KPIs or DORA metrics and so on that they can show from that side. We not only work directly with those teams, we also do and are looking for consultants and service teams that are maybe working with multiple clients and looking to simplify the work that they do with their clients. So also very happy to work with service companies on that side as well as the direct engineering teams and so on from that perspective. And then the very last thing before any questions that might be there is we do have a test drive. So not only if you want to do a pilot, but if you want to play around with Cape, we do have a test drive that can be spun up and you can play around. It has repos and has applications and clusters attached to it, so you can play and have a look. So for this, obviously a small sort of gifts for those that try it and send some feedback. Obviously, we would love as much feedback as possible. So please scan the QR and if you have time, please do spend some time in the test drive and reach out. So thank you. Any questions or anything in the room before I hand over? Yes, sir. So specifically, we do talk about ourselves being a CD tool. So we're not looking at the CI side. I mean, in the industry, we're seeing more of that move towards the CD, where the CI is becoming more and more inbuilt, and there's not so many specific tools. So specifically, we are on the CD side. So if you look at and specifically, we are focused on the Kubernetes world. So if you look at the sort of who we would see as competitors in the Kubernetes sphere. Uh, there are a lot of the areas that we focus on is the multi-cloud, being able to deploy anywhere, whether that is cloud, on-prem, right the way to edge, multi-architectures. That is one area that we do a lot of focus on. Out of the box, instead of bringing multiple projects together, those whole ideas about simplifying the progressive delivery, also looking at, I know as engineers, sometimes we don't like to look at it, but the approvals and the authorization side of things. So there's a whole approval engine that's built in there. So engineers can build out the deployments, but then have proper approval methods to do it. The authorization, so again, natively built authorization. So not only usually what you do with a service account, and then you see the service account has done the job, we can actually trace and see who the engineer was that actually pushed it to the service account and so on from that side. So there's aspects from that, which, yes, obviously you can do with Git actions and things like that there, but it's bringing that out to be more sort of team orientated, what the features are that larger teams want to work with and so on from that side. Okay, so if that's it, I would like to thank everybody and hand back. Oh, sorry. I have the wrong glasses on. I can't see too far. Okay, well, thank you. I'll hand back over. Thanks.
Oh, okay. Thanks.
Adjustments are being done. Someone wants to take break, you can. For 30 seconds.
Percent, right? Oops, how do I try that?
I think it should be outside. Yeah.
Should be?
Okay, the second presentation will be Ian and Yifrik. I will just hand over the mic to them.
How do I? Okay.
Okay. Hello, can you hear me? Hello, everyone. Thanks. I'm Li. I'm from DataTrack. So today, actually, I have my teammates with me. He's called Ian, our engineering lead, and we'll talk about the Kubernetes orchestration patterns, which Ian and team has built, and that's empowering one of our offering at DataTrack. And one of it is called batch jobs. So later on, Ian will talk about more details about how the underlying patterns work and how he designed it. So, and a quick overview, I'll just take the first 5 minutes to briefly share about an overview of what DataTrack is and what we are offering. And a quick overview is that we are the end-to-end MLOps platform that we simplify that you can see as a like Wix tool to build a website, but we are to build for a vision use case and deploying it simply for on different kinds of use case across industries. So that means that be it from pre-processing, that means the data preparations, annotating the label the data, and then to model training and to deployments as well. So we offer a wide range of what you need and customers use it for. And I can share some of the use case that's specifically for batch jobs today. So see it in a simple terms like this. So for example, usually when we call vision AI, that's what we teach machines to see, right? And from camera feeds, for video, for images, that is to feed into what the trained model has. So be it across like what you see here, for example, in agriculture, for example, in constructions, logistics, or even manufacturing, and some even in biomedical use case that has a big one. So some of our customers, they do have a large workloads that has to process maybe 100, 200 Ks of data in one go. And for larger models, imagine that has taken up like hours and hours. And what they have to do, if without managed infrastructure, they have to make sure that infrastructure is up. They have to make sure like latency. They have to make sure what if there is sudden error and the processing jobs can't be done in time. So that is what batch job is for. And a quick example is that one of our customers in the US, for example, they does AI applications that pair with like agriculture assistant that teach their customers how to build an home kit for hydroponics plants, for example. And all this means that each day they want to have insights or like AI suggestions for customers, and they want to have a fresh insights each day, and with fresh images coming in or videos. So this has a large needs for batch jobs at night that has to process, and when the next day their customers wake up, the AI suggestions or notifications will arrive, right? And that means an overview of how batch job will help them is that let's say they have a storage that's for images, and they will just need to submit the list of data set. So maybe I have 100K of images, maybe I have 200K, and I have 10 models, for example, and I just need to tell DataTrack, hey, this is a list of data set. Please help me to process with this model ID, and we will provide the processing. We will handle it for you, and share the results that is done. And you, with your webhook that connects back to your environment, and then when you wake up, you will be able to see all the results in your storage, and then handle it further for further processing and integrating back to your app, right? So a quick demo, recorded demo for what is shown here. So for example, I have an artifact that is for this model that I trained. And then I store my images that's to run through the inferencing on AWS and just drag and drop to generate out the dataset. And the dataset will just register with us on Datatrek platform. And with the webhook that is registered to us as well, and we'll just create the Bradshaw. And for Datatrek, you can see that the hosted platforms that we have here, one of the Bradshaw offerings will then have everything set up. And I just need a few clicks, right? Just now, when I upload it, and then fast forward, when the processing is done, then the next day when you wake up, you will see all this is being processed and all the results that's returned to on your site. So be it for monitoring status or email notifications, so this is what you get. And what this means, it just means that you can sleep peacefully at night, and our customers use it for all this managed service and then for all across all the different applications. So I think this is just an overview of what Batchjob does. And next, I will hand over the time to Ian. So he'll share a bit more in details of how the team has designed and he has led all this orchestration that make all this works. All right, thanks.
Here are the slides. Okay, all right, Ken.
Yeah, so as you guys have seen from the demo just now that Ife has done, there's a lot of different components that go into Batchjob orchestration. So the user first needs to begin by uploading the dataset that they want to perform inference on. And then they need to configure the webhook endpoint where they want to send the Batchjob results. And after these configuration items have been settled, we then need to focus on the orchestration of the compute resources that perform the Batchjob. Our Batchjob offering builds on top of the existing deployment offering that we've had for quite some time. And for this offering, we deploy users' deployments inside one of several Kubernetes clusters. So users can choose the US region or the Asia region to host their deployment. And to optimize performance and minimize latency during the Batchjob operation process, we decided to co-locate a Kubernetes job to perform the actual Batchjob task, which is to pull data out to the inference dataset, set it into the deployment, and forward the results out to the selected webhook endpoint that the user has previously configured. Now, you can see from this process that I've described to you, there's a lot of different components. They all need to execute in a very particular order. And if any one of those components fails, we either need to retry the operation, or we need to forward information about those errors onto our users so they can decide what they would like to do. Typically, the job of orchestrating workloads, custom workloads inside a Kubernetes cluster is done by an entity called an operator. An operator is like any other workload inside a Kubernetes cluster, and it performs orchestration via a process of state synchronization. So if we consider an example of an inbuilt workload in a Kubernetes cluster, a job, when we want to create a job inside our cluster, we start by defining an API resource, a job resource. And in the resource specification, we indicate the shape of the job. So how many pods it should have, what containers those pods should run, the resource request, etc. When the job controller sitting inside the cluster sees that we've created this new job resource, it synchronizes state by taking the specification here and creating the pods. These are the orchestrated resources. And the information flows both ways. So when the job controller sees updates to the pod status, it then takes that information and it reflects it back on the status of our job resource. But it's a curious thing, because even though jobs are dealing solely with this process of state synchronization, they need to be implemented in a stateless manner. And this is because, like any workload running inside a cluster, an operator can be interrupted unpredictably. And this can be for any number of reasons. So hardware failure, cluster autoscaling, or even routine upgrades can all cause an operator to stop temporarily. If an operator is holding on to some internal state that it needs to perform this orchestration process, after that restart, those orchestration tasks will fail. So we need to construct and define our API resources on the left and the orchestrated resources on the right, so that when an operator restarts, it can fully reconstruct its internal state and perform those orchestration tasks after interruption. And there is a key property of all the actions that our operator has to perform, which is the need to be idempotent. And this means that the effect of performing those actions more than once is exactly the same as performing those actions exactly once. And this vastly simplifies the implementation of complex orchestration tasks. If you imagine a scenario where an operator needs to perform 5 different tasks as part of orchestration, and it fails and it restarts after performing 3 of those tasks, because those tasks are idempotent, when the operator restarts, it can just perform all 5 of those tasks again. And even though the first 3 tasks are twice, it will have the same effect as those tasks being performed exactly once. Typically, you would store the API resource that I've been referring to inside the cluster. The Kubernetes API provides an inbuilt mechanism to extend itself. You can create a custom resource definition to define the fields, the resource spec, and the resource status. And the operator can leverage the inbuilt Kubernetes API functionality to read and update those resources. But there are some circumstances where it might make sense to store that API resource state outside the cluster. And one scenario where this is definitely true is when you have multiple clusters, as in our case. So we have an Asian cluster and a US cluster. If we had to store our resource state inside each of those clusters, then from our front-end dashboard and our CLI interface, we would need to query information from multiple clusters. And this complexity could scale as we add multiple regions. So if we wanted to add a Europe region, then we would have to query 3 clusters and so on. So it's much better for us to maintain a single API outside of all of our clusters where we can store this resource state. Another issue is that the Kubernetes API is optimized to deal with resources that are currently being used during orchestration. If you hold on to API resources long after they finish running, then these extra resources will slow down the performance of the Kubernetes API and decrease the performance of your overall cluster. But this directly contradicts the needs of our users, because our users want to see all the batch job records that they perform across time. So because we want to retain all of our inference workload resources long after they've been actually orchestrated, we again need to store them outside the cluster. And there are other client-facing interactions that are much better performed on an external API. So things like server-side filtering, the Kubernetes API provides a very limited interface for that. When you can imagine, as users accumulate many hundreds or even thousands of batch jobs, if they want to filter those jobs, we want to have that filtering capacity implemented on the server side, on the DB side, and not on the client side when you're dealing with that many records. But there's a key thing here, which is that if you're going to move your API resources outside the cluster, your API design needs to maintain certain Kubernetes-like structures that enable this efficient orchestration process. You need to keep those, and then for the rest of the Kubernetes API structures, you can decide on a case-by-case basis whether they are applicable to your use case. And to demonstrate that, I can provide an example resource from our inference resources API. So this is the broad structure of a managed deployment resource. This defines the deployment that I was talking about previously, that we create in the background, where users can create directly on our Nexus platform to run inference. You can see the structure is broadly similar to that of a Kubernetes API resource. So there's a kind, there's some metadata, there's a spec and a status, but there are some key differences also. So the Kubernetes API has a relatively flat structure. Resources typically exist either at the cluster level or the namespace level. And that's because that scoping system works well in Kubernetes. It doesn't work well for us because our resources are scoped into projects. So we have a different nesting structure, but we still need to permit like the Kubernetes API for cross references. And because our API resources have different nesting structure, we maintain a single field that enables us to do cross reference. And identity is also very important. Here we can leverage existing standards in HTTP to enable idempotent requests. And this is why we have this ETAG field. ETAG is essentially a SHA-256 sum of the resource contents. If an operator, for example, wants to update the status, we can specify in a header in our request if match ETAG. And that means that request will succeed at most once. That's because if the request succeeds once, the ETAG of the resource will change, and then the subsequent requests fail. And we also need to permit for the storage of custom metadata. When we're designing the structure of APIs, we don't necessarily know upfront all the information our operators will need to hold on to when they're performing orchestration. So we need to provide some place for operators and users to dump metadata. In Kubernetes, this would be metadata.annotations, but because we're a computer vision company, the term annotation is a bit overloaded. So we went for attributes instead, but the concept is the same. And like in the Kubernetes API, we have separation of desired state on the spec and actual state on the status. And this makes it clear for API users and also makes it easier to implement things like RBAC and other authorization control. And one important thing for interactions with this API is that we need an efficient way to detect changes. As our deployment operator is running, it needs to know when users create new deployments, update existing deployments, and remove existing deployments. There's a lot of different ways you could do this because we're working outside of the Kubernetes API interface. So you could use a message broker for this, like PubSub or SQS. We took a page out of the Kubernetes API book and built it directly into the API. And we have an interface which is broadly similar to the Kubernetes Watch API. The implementation of a Watch API outside of the scope of the Kubernetes API and its CD is outside of the scope of this talk. But if you're curious, you can come talk to me afterwards. I'm happy to discuss in more detail. And all this information is going to get fed into our operators. So to provide an example of how our operators work, we can take the case of the batch dump operator. It's broken down into three main components. First, on the left, we have a set of watcher threads. And these are going to leverage our existing API interface that I just mentioned. We take in updates about all the resources that are used in batch dump orchestration. So we have a batch dump watcher, we have a dataset watcher, we have a deployment watcher, and we have a Kubernetes API watcher for the job resource that defines our batch dump runner. The information from all of these watcher threads is going to get fed into a single in-memory data store. Now, you'll note we are holding on to internal state, but it can be entirely reconstructed when the operator restarts, so it's perfectly okay. And all the information in the data store is then going to be used to enable reconciliation of the state of all of these different resources. And we have one key invariant that we use during this orchestration process, which is that we apply at most one update to any resource at any given time. Why? Because we're dealing with a lot of different resources. If we simply fired off an event whenever we received a watch event from any one of these resources, we could have multiple concurrent executions of orchestration tasks for a single batch job, and that can ultimately lead to an inconsistent state. So it's much easier if we simplify this and say, okay, we're going to do one thing at a time. And that makes it easier for us to be sure that our implementation is correct and that we're executing in the correct order. You might wonder about scalability. It's a valid concern, but note that the invariant here applies to the resource level. And that means that if we have too many resources to execute within the context of a single reconciliation, we can just set multiple loops. We can divide the loop of batch jobs for orchestration across several reconciliation threads, and we can scale that way without violating this very important variant here. In terms of the data store, its structure is also important. We're not merely collecting information about the different resources, we are also grouping them together. And this is because when we are performing orchestration tasks, we are not merely concerned about the state of the individual resources, but how that state relates to each other. When we're orchestrating a batch job, before we even are worried about the deployment, we need to first think, is the data set uploaded and has been processed by our backend? So the relationship, for example, between the batch job and its data set is very important. And this is where these cross references come in. You'll see in the batch job spec, we define a reference to the data set. So when updates about that batch job and that data set come into the operator, we can associate them together in a single group. The same is true for the deployment. Now, when we define the managed deployment resource, when we first created our deployment offering, we were not thinking about batch jobs, but that's okay because we have our metadata attributes field to store custom metadata. So we can insert a reference to the batch job there. And the same is true of the Kubernetes API. So for our batch job, we can insert a batch job reference inside the metadata annotations. And there's one last key thing to consider before we can focus on the actual orchestration tasks, which is the status conditions that we're going to define for each of these resources. And here, the status conditions must reflect key transitions in the resource lifecycle. So to provide an illustration of this, we can take the dataset case, which is the simplest. The dataset resource undergoes two key transitions in its lifecycle. First, it's uploaded by the user, and then it's processed by our backend. So you'll see our API defines two possible status conditions for the dataset resource, uploaded and processed. And we also are concerned about the relationship, again, between these different resources. You'll notice that the process condition here, in terms of batch orchestration, is the most important. From the point of view of the operator, I don't really care if the data set is uploaded or not. I care that it's been processed. So this final status condition is a bit special. We refer to it as a terminal status condition. You'll see that we relate these two resources by bringing the terminal status condition and defining it as a separate status condition of this resource here. Now, we are sort of tangentially concerned about, for example, the other status conditions like uploading, in the sense that if we take the totality of it, we're concerned about two things. A, has our related resource reached its terminal status condition? Or B, is it possible for that status condition to be reached at some point in the future? And this is why we care about uploading, because if upload fails and times out, we know definitely not gonna be processed. So we can reflect that error down here. And the set of these different states of our system can be modeled as a finite state machine. And this is important because now we've taken this complex thing, which is how can I make sure all these different things execute in a particular order? And now I've broken it down into something manageable. I can think about all the possible different status conditions that these objects can reflect during the orchestration process. And the transitions between them are done on a step-by-step basis. So we can implement the orchestration tasks on that step-by-step basis in our reconciliation loop without violating our key invariant that we perform at most one task for each iteration. And I can show you how this works by stepping through with this example batch.resource. resource. So this represents the initial state of like 95% of the batch.resources resources that are going to come into our operator, because most users will have already uploaded a data set before they create their batch job, and the processing happens relatively quickly. So when you get a new batch job, the operator is going to see the API has started us off with a waiting status condition for data set process, and the data set is already been processed here. You can see for the first iteration of our reconciliation loop, we have an inconsistency. Data set processed here, but not here. So our single action is just to set the status condition here, so it reflects this one. And you can set multiple status conditions in a single API call. So we help ourselves out a bit and set a waiting status condition for the next phase of batch orchestration, which is creating the deployment. And now on the next iteration, we have another inconsistency. We are waiting for the deployment to be provisioned, but we have no deployment. Okay. Well, we just make a single API call to create the deployment. And this here illustrates the principle, another key principle of Kubernetes, which is resource composition. From the point of view of the batch operator, we have no idea how the deployment creation works. We are interacting with this object at an API level. We can leverage all of the existing work that we put in to enable deployment orchestration. And here, we can just model it simply as an API object. Now, the deployment is going to have in the real world a lot of different status conditions. The terminal condition that we're cared about is ready, which means the deployment is online and able to accept HTTP requests. So in our example scenario, it becomes ready after some time. And we have another inconsistency, as with the data set. Deployment is ready, but it's not reflected down here. So our single action is just to reconcile those two states. And then we enter the waiting state of our final status condition for the batch job, which is to finish. And here we have another inconsistency, which is now we finished creating all the sub-resources that we need to worry about for batch orchestration. Now we have to actually do the thing. So we do that by creating the Kubernetes job. The Kubernetes API status conditions work slightly differently from those of our internal REST API. So our internal REST API, the status conditions can have three states, as you can see here: finished, waiting, or error. A Kubernetes job that's running will typically have no status conditions, and then it will reach one of two terminal states. Either you will have a completed true status condition, which means the batch is finished, or in our example case, we encounter failure. So maybe the bug endpoint has rejected some of the requests, and the batch job should ultimately be considered as failed. And now, from the user point of view, we have our final inconsistency, which is failed here, but not here. So again, we reconcile by just taking the status and bringing it over here. And at this point, the user can see now on our dashboard, or for example, on eFace Streamlit app, that the job is failed. But there's still one final inconsistency here, which is we created this deployment as an ephemeral deployment for that job. Now the job is finished. We need to get rid of it. The task of getting rid of the deployment still falls under this concept of reconciliation, because there's another inconsistency here. The batch job has reached a terminal state, but we still have its associated deployment. So again, we can perform a single action by making a delete API call. And now we're really done. So you can see by modeling this complex orchestration pipeline as a series of state transitions, we've greatly simplified its implementation while still ensuring that we execute all the steps in the right order, and we can reflect error information back to the user. But there's one final piece of the puzzle, which is fault tolerance. So most errors that you're going to encounter in production after you've ironed out all the application level bugs are going to be transient errors. Meaning if you try them again, typically it will succeed. And deployment provisioning is a great example of this because GPUs are so popular. If you request for a GPU pod in your cloud Kubernetes cluster, sometimes your cloud provider will get back to you and say, nah, actually not, right? But if you just wait a few minutes, then typically you'll be able to get those GPU workloads executed. From the point of view of our users, it would be really bad if we encountered one of these transient failures and just stopped and said, actually, we couldn't execute your batch job, right? One of the things they're paying us for is to handle all these little transient errors. The question is, how can we fit in this fault tolerance into our sort of state machine idea of thinking about this system? So when we consider how this orchestration process can be modeled as a more traditional state diagram rather than the animation that I just showed you. The deployment rollout represents three possible states. So we go from the data set process state, the terminal state here, and then we enter the rolling out state. And we can go back from the state to itself as we're waiting for the deployment to roll out. And then ultimately, we're going to reach one of two states, which is either the deployment becomes ready, and then we can proceed with the rest of the pipeline, or deployment rollout fails. And then we need to figure out what to do here. The naive approach would be, okay, we have a callback for this. We have to add our create deployment code back up here so that we can implement a retry. But that's not great because now we're duplicating code logic. And then we have to think about other things like, oh, should we retry or not? And so then this handler is going to get quite complicated. The key thing to realize is that we already have the logic to create deployments down here. It would be really great if we could reuse that. And the way to do that is we need to figure out how to go from this deployment failed state back to our data set process state. And the key difference is that here we have a deployment and here there is no deployment. All we have to do is create a loop in our state machine. Just make a single API call here to remove the deployment, and now we're back here again. And we can then we can affect this loop and ensure that we have massively improved default tolerance across the system. Okay, so that's a lot of content. So what should you take away from this? First, if you are dealing with a multi-cluster architecture or there are other product system requirements you have, then you can consider storing your API resources outside of the cluster. But if you're going to do that, you need to adopt certain key principles of the Kubernetes API to enable efficient orchestration. And finally, if you model your operator behavior as a finite state machine, you can simplify implementation of these complex orchestration pipelines while still maintaining a good level of fault tolerance. And I think we're out of time, but if you're curious, you can talk to your DFA if you have questions. You can connect with us on LinkedIn. And if you're curious about finding out more about the Bastion operator, you can talk to us as well. Thanks.
Once again.
Oh, go ahead. Yeah.
Yes, thanks for the sharing. And could you go back to the orchestration steps?
Cheers.
Yeah, this one. We can see there are kind of four parts. In every part is connected with each other. I'm wondering what is that triggers to let the next step know, oh, I already finished, or I'm falling now.
So that's a good question. So the question is, how do we know to trigger these different actions? And the trigger point is the inconsistency. So we go back here. So here's an inconsistency. The API resources are going to come in a certain state, right? So they're going to come in. This is an example of like what the operator is going to see at a particular moment in time. And there's an inconsistency between this resource state and then here. So that's how we know there's a trigger point when there's some non-alignment between the two resource states.
So you mean consistency, so you mean if you deploy it into the cloud, like the AWS, do you use any specific service to set this trigger?
No, so we are relying purely on the API changes coming in. We have like an event stream, essentially, that allows us to receive all this information.
Okay, thank you.
All good. Okay. I think you explained very well.
So anyways, if you guys have any other questions, they are still here, so you guys can reach out to them. Or you can reach out to them on LinkedIn as well. They have shared the QR code and everything, so it's already there. So yeah, thank you very much, Aoife and Ian.
Yes.
Yeah.
So now.